continuing on with our parallel to the alkenes, we're going to look at what happens when we do a hydration reaction. Now, if you remember, we had done this two different ways and gotten two different products out of this. If we did the oxymercuration, what we ended up with was the more substituted alcohol. If instead we went with the hydroboration, where we had a hydride, an H minus, as part of our explanation, we ended up with the less substituted alcohol. So this was the hydroboration. Well, we're going to have the same problem here. We're going to do a similar problem. We're going to choose an alkyne for starters that's unsymmetrical, specifically one that's terminal, and we'll talk more about that later. If we do something similar to oxymercuration, we're going to end up with an oxygen on the more substituted carbon, the one on the left is drawn here. If we instead do something analogous to hydroboration, we're going to end up with an oxygen attached to the carbon on the right. Here's what that looks like when we're done. In one case, we end up with a ketone. In the other case, we end up with an aldehyde. Notice I carefully said we ended up with an alcohol on those two carbons. So, let's talk about how that actually works. So mechanistically, they're going to be very similar to a point. So if we look at the oxymercuration, it's going to look exactly like it did before. So first step is we're going to use a slightly different mercury compound, mercuric sulfate this time, and sulfuric acid and water. And we're going to end up putting the oxygen on the more substituted carbon. So mechanistically, just as we did before, we're going to end up attacking the mercury. That's going to give us something like this, where we're going to have the mercury on the terminal end, and its attachment to the sulfate's a little different into an acetate. It's more ionic, so how that's actually working out, this is probably going to be a +1 at this point. And then we're going to have a cation here, so technically that still should be sp hybridized, so really it should look like this. We shouldn't be drawing the angle if it doesn't have one yet, so it should be this. So again, questions about how this is going to happen, but we're going to end up with a nucleophilic attack of water. So that's going to give us what will eventually end up as our oxygen. But it's coming in just as it did in the alkene case, as a protonated water molecule, as a protonated alcohol. So we're going to have another water molecule taking care of that. And that leads us to here, where we now have something a little bit more sensible, an alcohol. Now, notice when I put this up first, I said that's not what we end up with. In the alkene case, the mercury, through a long and drawn-out process, ends up just replaced with a hydrogen. That also is true here, but that's not good enough. It's not telling us what we need to know. It's not getting us to the answer that we are looking for. It is not explaining what we want to know. So, how does it work? All right, it's important to remember at this point that we still have strong acid around. So, we tend to draw it as if it's coming from the hydronium. This is how your book approaches it, that we're actually getting something like this, so that we end up with another H on the terminal carbon and a cation at the more substituted carbon. And if we look at it that way, we can say a couple of different things about this. The mercury apparently is going to give up the electrons it's using to form that semi-covalent bond there and give us a stable non-mercury alkene. So that we have the alcohol that we thought we should have gotten all along. But this is a very particular alcohol. This is called an enol, and they are not typically stable. Because, very similar to what we just saw, the alkene can pick up a hydrogen, and when that happens, we end up here with yet another cation adjacent to the oxygen, but now I have 3 hydrogens on the terminal carbon. I have lone pairs here, not too difficult to see what's going to happen. The alcohol can donate a pair of electrons, and then we have a pi bond. Now, over here, it's now just a methyl group. So, 3 hydrogens. Last step, well, water will take care of that. And we're here. We now have a ketone. Specifically, we have a methyl ketone because we started off with a terminal alkyne. So, if, on the other hand, we had started with something that was not a terminal alkyne, so if we'd started off with something like this, well, we'd end up with a mixture of places where the ketone ended up. We'd end up with this, where the ketone ends up on the left carbon, and we'd end up with this, where it ends up on the right one. So we'd end up with mixtures. We really wouldn't want to see that, so it wouldn't be necessarily a good reaction to use unless we have clear asymmetry, meaning a terminal alkyne, or we have a molecule that's actually symmetrical. So if I did the same reaction here, well, it doesn't matter which one it goes to, there's only one product. So at that point, it is this. No matter which one it reacts with, I'm getting the same product out of it. So those are the cases where oxymercuration is useful. Its mechanism is ugly, but it's doing the job that it did in the previous alkene version, exactly the same way. The other case, as you might expect, is working exactly opposite to that. So if we're looking at something on the terminal alkyne again, with the hydroboration, well, we did that with alkenes, we did it with BH3. So we used this and coordinated to something like THF, and we ended up with this, where we had an H on the internal carbon because it was nucleophilic. It was a hydride. And we had an intermediate boron here. And there were still the 2 hydrogens from the original alkene. And then this could go again and again, and then we ended up with hydrolyzing it off, and that became our alcohol. Well, here, we'd really rather not do that if we don't have to. We'd rather just get on with our job. So what we typically use here is a different type of boron reagent. Usually we use something that only has one H attached. So something that has 2 other groups like this. Things that can't do anything else but, just don't get in the way and don't end up with us getting multiple alkynes too close to each other. So here's what that's going to look like. There are a couple of examples. The one that seems to come up a lot is a dicyclohexyl version. So we have a couple of chairs drawn here. So I'm not going to draw them right now. We'll just make this quick. Or what's called 9-BBN, which is ugly. 9-BBN is kind of an awkward looking beast because it kind of looks like 2 chairs that have been slammed together. But in the middle, bridging up above it, is a boron. So it basically has no real ability to interfere, and it can only undergo the reaction once. So we end up with, for the exact same reasons that we had in the prior case, hydrogen on the more substitute of the 2 carbons and the boron on the other. So if we do this, we're still undergoing a relatively symmetrical reaction. So we're looking at this and having this happening basically simultaneously. So attacking the boron and the hydride attacking here all at once, leaving us to this, where now we have the boron, I'm just going to abbreviate that as R2, and the H in place. And as before, we're going to end up hydrolyzing the boron to give us an oxygen ion. Now, this case, again, a little more tricky. It's not going to come down to being quite as simple because these are not acidic conditions. In the mercury case, we had an acid present the whole time. We don't have that here. Specifically, our conditions here are hydrogen peroxide and sodium hydroxide. This is basic. So you don't go drawing acid mechanisms in the presence of sodium hydroxide. That's a good way to lose points. It's a good way to be wrong. So as before, when we did this in the previous chapter, we have an insertion going on. So we have our alkene here, and the boron and its its large friend, the rest of that ring that we had drawn before, and we end up with this hydroperoxide ion with the peroxide and the sodium hydroxide, and we end up doing exactly what we did in the previous chapter. That is, inserting an oxygen into that boron to carbon bond, because we're going to end up first going here with this, and then having it rearrange as before. So we end up at the end of the process looking like this. Now, when we did this with the alkenes, we didn't really concern ourselves much with this. We just kind of looked at it as saying, okay, we'll finish off the hydrolysis after the reaction's over. We don't need to do that here. If we attack this again, the boron again with sodium hydroxide, what we end up with is this. Eventually, and it's not an SN2, but for simplicity's purposes, let's just draw it as if that's what it does. It will break this off. So we end up here with an oxygen anion. What happens next, your book calls this tautomerization, which I don't really like calling it that because that's not what it is. This is plain old simple resonance. We're forming a pi bond and breaking another one. There is no tautomerization. Tautomerization involves moving a hydrogen around. That's not what's happening here. This is just resonance in its pure simple form. And there's the aldehyde we're looking for along the way. And we now have a negative charge here. And since we're dealing with sodium hydroxide, then we're almost certainly also dealing with water, and this is considerably more basic than water, so we're going to end up protonating that relatively quickly. So that what we're left with when it's over as our product is this, the aldehyde. Now, as before, if I did this with something symmetrical, I would still get only one product. If I did this with something unsymmetrical, then just like the oxymercuration, I would end up with multiple different products. And so neither of those reactions is great if I have an unsymmetrical alkyne to begin with. They really have the most use if I either have a symmetrical alkyne like the top one here, or I have a terminal alkyne like the example we began with, because it gives us only a single product.